Hi people, this is Gleno speaking. Welcome to Flat Earth discussion. Okay. Today I'm doing this video when I got some spare time on my hands with no one around. I thought I'd do this and finish it off because when I did my first video I had said to some people that I was hoping to get another video out by last week, and that sort of didn't happen because I found that I had a lot more research to go into, okay, as will become evident as you keep watching. Alright, now I'm going to deal with two different topics in the course of this video. I could have split it up into two different videos, but I decided to lump it both together, so bear with me, okay. Alright, so the first topic I sort of want to deal with is the accusations that are thrown at the flat earth formula for finding curvature drop 8 inches by miles squared. I want to have a look at that, the accusations against that, and show how they're not right and how the approximation is pretty good. Okay, and then the second part I'll be dealing with local gravity, you know, because the Earth's spinning, right, rotating. It's more of an oblate spheroid according to the theory, and as a consequence the equator is bulging and the poles are flattened, and as a consequence of that, gravity is lighter at the equator than it is at the poles, and as a consequence of this, then the theory goes that things will weigh less at the equator than they do at the poles. Okay. All right. So as you know, I've done a lot of research. Whereas, you know, there's a lot of people out there who are trying to debunk flat Earth, and they do a lot of research, they say, but they're looking at you know, how to debunk flat Earth websites, and they're pretty much coming up with the same rubbish. Okay. And it sounds to me like they're just getting stuff from these kinds of websites. And as you notice, some of these aren't even atheist websites. They're actually Christian websites trying to debunk flat Earth. So it's not just a Christian thing, this flat Earth thing. Compare it to my research, it's all handwritten. There's a lot of work that's gone into this. So just hang in there, okay? All right, so the two frequent accusations that are directed at the flat Earth curvature drop formula is: one, it's not accurate, and two, it's only accurate up to 100 miles. Okay, so we'll have a look at this. Now, I can't think of any flat earthers who would claim that it's anything other than an approximation, whereas the scientific community would be saying, well, approximations aren't scientific, you can't use them. Well, how about pi? Pi is only an approximation, right? For example, if we take the mean radius of Earth and then we multiply it by 2 pi to different decimal places, we get these different numbers, right? So for 3,959 miles, if we multiply that by 2 by 3.14, we get 24,862.52 miles. And if we go to the next two decimal places, we get 24,874.397 miles. So the more decimal places you get, the bigger the number will get. But then eventually, because of the decimal places, they will you will end up rounding up to a good approximation, a good proximate number, right? So but the reason why it's only an approximation is because you're trying to fit a triangle into a circle, right? I mean, as Euclid would say, cos triangles. That's the problem. That's why it's only an approximation. And he wouldn't be the only person who's tried to, like, fit squares or triangles into round holes, right? Okay. And another approximation is you get this dude called Bill Nye saying there's way more stars than grains of sand on every beach in the world put together. He reckons he's counted. But anyway, he hasn't really. But he acts like he has. Have a look at what this Australian dude's done. Use estimations, right, to find out how many stars there are, then how many grains of sand there are, right, in order to come up with his theory of how many grains of sand compared to stars in the sky. And he admits that he uses it's estimations or approximations, yet he calls himself scientific. Right. And here we have Bill Nye, who's saying he's on Logan's Beach in Warrnambool, saying he's there to count the sand. Yeah, well, you can't use approximations. I mean, that'd be almost like looking at Australia, then looking at Japan and UK and saying there's more people in Australia because it's bigger, all right? Then you find out there's only 24.4 million people in Australia compared to 126 million in Japan and 65.4 million in the UK. Okay, then you have a look at this and which ones are correct? You know, they can't even get the radius right, you know, of their Oblate spheroid. So anyway, all right, so this is the formula that they use, right? And what they don't show you or concentrate on is the trigs, which I've circled here. But I don't think they claim that it's even 100% accurate. It's just an approximation. That's the old version, and then they've updated the version to give it up to 3,959 miles. And you can see the trigs version down the bottom there, right? And so we're going to use those two, the 8 inches by mile squared. And then we're also going to compare it to the trigs formula. We're also going to compare it to this dude. He's saying that flat earth, his math is wrong, right? 8 inches per mile squared, it's wrong. That's what he's saying. And this is his approximation. Right? Drop equals the square root of radius squared plus distance squared minus the radius. So we're going to have a look at that. Then we're going to compare it to this geometry that I got off, which a lot of curvature formulas use, this sort of thing. So we're going to be interested in 4 main measurements here to do with drop, okay? Okay, so the actual parts we're going to be looking at are M, N, D, which is the drop, and C, which is that angle in the middle, which is A plus B equals C. M is the sine of C times the radius. To find out N, it's 2 times the sine of C divided by 2 times the radius. The drop is the square root of N squared minus M squared. And of course C, that angle in the middle, we take the C, which is the distance, the little c, we divide that by the circumference, and then we multiply that by 360 for 360 degrees. So that's how we work out those lengths and that angle. Okay, so we're going to be looking at these, and we're going to look at that drop, because the other parts of the equation, they look at the height that is hidden, okay, which is y, the y over in the right hand corner there. These are the angles and the distances we're going to be looking at. All right, so let's take a look at the following 2 formulas and compare them with the approximation. Okay, we're going to have a look at this, and we're going to see how accurate they are, and then we're going to compare it to my geometry. All right, okay, let's do it over some small distances. So we're doing it over 49.27 miles. The 8-inch formula gives us 1,618.3552666 feet, right? The square root formula gives us 1,618.70137 feet, right? And as you can look at the other equations and my own geometry, you'll notice, if you pause the video, you'll see that Dropkick here is, I'll call him Dropkick or Dipshit, his square root formula does happen to be a bit closer, right? Now we'll look at 63.71 miles, and Dropkick's is still closer to the geometry, okay? But we're going to go a bit bigger. I'll get you to pause the video and just do the maths and look at the numbers yourself, okay? We'll go bigger, and now, as you can see, over 119 miles. Dropkick's formula is a bit closer still than the 8 inches by mile squared to the actual geometrical equation, okay? But we will go even bigger than this, okay? I'll have a look. And then we look at 147 miles. Again, it's a better approximation than dipshits, okay? it's a much better approximation. It's actually closer to the geometry, okay? And then we look at even a bigger number, 243 miles. Dipshits is off, okay? It's off, whereas the 8 inches is a pretty good approximation, okay? It's even closer to the actual geometry, okay? So it's a good approximation at 243 miles compared to his. Then we look at 749 miles, and again, the 8 inches by mile squared is actually closer to the geometrical result than dipshits, okay? It's even closer than his to the actual right number. All right, now let's go even silly, 2,473 miles. And as you can see here, dipshits square root formula doesn't even come close to the actual number compared to the 8 inches by mile squared. Okay, so for 2,473 miles, you get a big difference between these three formulas, right? And it looks like the 8 inches by mile squared is actually closer over longer distances than his silly formula, all right? Dropkick, right? So Dropkick's approximation seems more accurate over shorter distances, but the 8 by mile squared is definitely a good approximation for longer distances. And of course, as you can see by this, I mean, over a 90-degree angle, you're not going to be able to see anything past a 90-degree angle anyway. So is this correct? No, it's bullshit. Okay, so we're going to look at local gravity and international trade next. The reason why I'm focusing on this is because other people have done stuff, you know, have answered other questions. Like Adam's Truth Journey here, he's looked at how sunsets work on a flat Earth, right? As you can see, the further away behind the refraction sheet that he's pulled his lighter, the lower the flame and seems to be, and even the lighter itself seems to disappear, even though it's on a flat plane, right, on the table. So, you know, there's no point going over what other people have said, okay? I wanted to find my own niche, all right? But he's done a good job here. He pulls away the sheet and he shows the light is still there. And then you got people that take on NASA, like, you know, Flat Earth arsehole. You know, I don't need to take on them. And then you've got people like Antarctic Warrior here, and see how he shared my video and it's got over 1,100 views. Beautiful. Yeah, I'm not going to go over the same sorts of stuffs. I'd rather do my own stuff. And here we've got some of the basis for what scientists base their so-called globe theory on, you know. The work by Isaac Newton, talking about different gravity, and he's talking about how the equator is bulging and the poles are squashed, you know, because he's compared it to Jupiter. So he's looked at Jupiter and he's seen observed that it's squashed and at the poles and bulging at its equator. So we must be the same. That's what he's sort of come to. And then he talks about how it's the latitude, you know, and the increase of weight at different latitudes, you know. So passing from the equator to the poles is nearly the reverse sine of double the latitude, or which comes to the same thing as the square of the right sine of the latitude, all right? So that's what he's talking about here. He's saying that between the equator and the pole, that there's a loss of weight between the poles and the equator. And here he's talking about the accelerated force, you know, and talking about the weight in different regions, and talking about elevation in higher regions, how elevation even impacts gravity, right? This so-called thing, you know, all based on pendulums, okay? And so he's always going to say cos local gravity. So I looked up some local gravity stuff, right? Got this dude, he's asked an astronomer, you know, 7th grade student, he's asked him, you know, is it true that you weigh less at the equator than at the poles? And this dude said, yeah, you're actually right, yeah, because of centrifugal force. But then he admits there that centrifugal force is a fictitious force, and it's got to do with the rotating frame of reference. And then we've got some other calculations to show what standard gravity is and stuff, and some other things to do with an oblate spheroid. And it says with the radius at the equator slightly larger at the radius at the poles. That's what he's trying to say. Okay, so let's have a look at the local gravity formula. All right. Okay, so let's have a look at this local gravity formula and its breakdown. Okay, so if we look at the first part, as G, which is gravity, or represents local gravity, equals 9.780327 times 1 plus 0.00533024 times the sine of L, which is squared, minus 0.000058 times the sine of 2 times the latitude, and that's squared. Okay, that's the first part. That's the international gravity formula, all right, of 1980. It's meant to determine gravity at a given latitude where L is the latitude, all right. The second part is minus 3.086 times 10 to the power of -6, and then you times that by the height. All right, this is the FAC, or the free air correction, which is meant to correct for height or elevation. All right, so let's have a look at this. Okay, we'll put this on oblate spheroids. We've got the original theory on the left. It gives the North Pole at 90 degrees. What they say in those articles I showed you is that at the North Pole and the South Pole, the gravitational acceleration is 9.832 meters per second squared. At the equator, which is at 0 degrees, it gives it the gravitational acceleration is 9.78033 meters per second squared. And then we go to 45 degrees latitude, plus or minus the equator. We get a standard gravity of 9.80665 meters per second squared. Now, if we actually use the calculations, it does represent this pretty accurately. I mean, you go and have a look at the North Pole, 90 degrees, and it's 2 meters elevation, and we're talking about like 1 to 2 meters thick of ice on top of water. Okay, so that gives us 9.8321258,417 meters per second squared, gravitational acceleration. And if you have a pause this video and have a look at all the rest, you can work this all out yourselves as well. And you can see that going by this, it does sort of represent quite accurately the gravitational acceleration at given latitudes and elevations of an oblate spheroid in a rotating frame of reference. So theoretically it works, but does it work in reality? Like, does it represent what we see in reality? And that's what we're going to look at in the context of international trade, okay? We're going to look at that next. Let's have a look at part 2, which is the international trade and local gravity. I'm going to show you how international trade would be affected by local gravity. Some people write this off as insignificant, you know, like it wouldn't have much of an effect. But, you know, if in the context of international trade, once I show you the figures, I think you'll see that it would have a big impact. Okay, so I did some econometric research. Okay, I looked up, you know, gravity and its effect on international trade, and I only come up with a few articles here and there, and they basically don't even talk about gravity as such, other than as a constant. So they don't even look at it at a local level. They're more interested in like distance and costs to do with importing, okay, as some of the main reasons why they don't. It shows to be a bit smaller than intracontinental trade, okay. There are other factors. For instance, in Malaysia, you know, for a while they stopped importing our poultry because of the bird flu, and there are other, you know, reasons, you know, like the US had a bit of a scandal where 2 suppliers weren't supplying real halal beef, and so they preferred to buy from Australia, okay, whereas you get other countries that'll prefer to buy from the US because, you know, their beef's probably $2 US cheaper than Australian meat. So there's all sorts of different factors that need to be looked at, but one of them that would need to be looked at if it was true would be local gravity and its effect. Okay, now as you have a look on here, it shows you his references that he uses, and one of interest to me is there's one here to do with the gravity data, right? And so I looked up this gravity data thing. Okay, as you can see, I have done a lot of research, and it talks about the gravity, and it talks more about the distance and the amount being exported and stuff. It's got nothing to do with actual gravity. Okay, so this is actually new territory. I'm breaking new territory. I'm a pioneer in this. So hopefully, if you wanna talk about local gravity and its effect on international trade, you can come to this video. This is it. But I'm going to show you how it doesn't. All right, how it does not affect international trade, mainly because it doesn't even exist. Okay, it's bullshit. All right. But anyway, so it talks about the trade flow and economic mass of each country and the distance. And it says treats G as a constant, all right? So I looked at, started looking at our meat exports, all right? And as you can see, here's all the different lamb and mutton and beef. I looked at all the different countries that we export to. Then I looked at carrots and all sorts of stuff. I've done a fair bit of reading. So anyone who says I don't know what I'm talking about, just have a look at what I've looked at, all right? You have a look at it yourself, and you see if... I even looked at buffaloes, right? So I start off with a cow. I thought beef, yeah, we'll look at beef exports. And so I looked at... I even looked at shipping routes. Right, this is an interactive one, and it shows that there's a lot of international trade. It's actually going against their own thesis. They're saying there's not much international trade. This is showing a lot, okay? And you can even look this all up yourself, and it's pretty cool. All right, so they say there's a 0.5% weight difference between the equator and the poles. So if we divide that by 90 degrees, we get 0.0000555556 of a kilogram weight difference per degree of latitude. If you're wondering how I came up with that, well, I just multiply 1 kilogram by 0.5%, right? And you're left with, it gives us 5 grams, okay? And if you divide the 5 grams by 90 degrees, you get 0.00055556 of a kilogram per degree of latitude, all right, between the equator and either pole. All right, and why is this? Because local gravity. Moo. All right. So, sorry. Anyway, we'll look at Charleville. and Kuala Lumpur and Jakarta, right? I take the latitudes of Kuala Lumpur and Jakarta, and I subtract them from Charleville, which is in Queensland, all right? And then what I do is I multiply them by the 0.00005555556, which gives you the difference, latitudinal variation of a kilogram, right? And then I looked at the meat sales to Malaysia and then to Indonesia in tons. I then converted them into kilograms later, but I show how I divided by 365.25 days to show how many kilograms per day, right? And then I did the maths, and I did the maths to show the difference between how much it weighs in Australia and how much it weighs in Jakarta and Kuala Lumpur, respectively, right? And then I did the maths to show how much they lost per day, and then I have a look at this. All right, you can see the tons that it weighs, how much it weighs in Australia and how much it weighs in Kuala Lumpur or Jakarta. There is a problem. They're missing some tons. So let's put it in economic terms, right? For a loss for the year. As you can see, one's lost $95,000 worth, and the others lost about $263,000 worth, right, over the course of the year. All right, and all because of local gravity. Moo. I call bullshit. Okay, it's rubbish. All right. Anyway, so I looked at lamb as well as mutton, right, because it wasn't giving me the figures I was after that I thought would be persuasive. Okay, and I did also over a 5-year period to try and get some bigger figures. All right, then I looked even into wheat and tried to look over that, and then poultry over a 5-year period. And then I even looked at buffalo, which I talked about earlier, and then even seafood. I looked at our seafood exports, okay? And then I looked at the goat export, which seems to be increasing, and sugar even. But even that wasn't giving me enough, so I went for carrots. All right, looked at carrots. I looked at this over a 5-year period, and also from different places like Papua New Guinea and Singapore, etc. So it wasn't just Jakarta and Kuala Lumpur. And it still wasn't giving me the numbers I thought would be persuasive. So I thought gold. All right, that was my next thought. Try gold. So we're going to have a look at the international gold export data, all right? We're going to look at export between UK and Switzerland, then Switzerland and China, Switzerland and Hong Kong, Switzerland and India, Switzerland and Thailand, Switzerland and Singapore, and Switzerland and the UAE. And I got this data from the goldcharts.com website, okay? So I've got all the latitudes here of the capital cities. Could have used Shanghai instead of Beijing, but I thought Beijing gives me a smaller number. You know, Shanghai being further away from Switzerland would give us a bigger number, so I went for Beijing. All right, so the method for calculating the local gravity, right, and the impact of it on international trade, I take the latitude of the exporter and subtract the latitude of the importer, right? In this case, UK, and we subtract the latitude of Switzerland, we get 5.1757. And then we multiply by the weight variation, right, of 0.000555556 per degree of latitude, and it comes to this number that I multiply by the dollar amount, which gives me the loss incurred over those 5 months, okay? And then I multiply the net weight of the gold exported in kilograms by an average price per kilogram of $53,350 AUD. Then I multiply the amounts paid by latitude variation calculated to find the loss. And then finally I add loss from gold export transactions for each month to find the total. Now we have a look at this. This is where I got the information for price per kilo, $53,350. It was higher, so I went with the lower number. So no one could say I used too high a number. Okay, all right. So let's do some freaking maths. All right, let's do this. Okay, so looking at the transactions between UK and Switzerland starting from November 2016. In November they exported 46,100 kilograms, and we multiply that by the dollar amount and we get a loss of $707,000, right? Okay, and then we go to December. There's 151,900 kilograms, multiply that by that dollar amount, and then we do the maths, and it gives us a loss of over 2 million, right? 2.3 million. Okay, then we look at January 2017. Exported 84,400 kilograms of gold. All right, and that gives us a nice loss of $1.2 million dollars worth. All right, and we look at February 2017. 30,700 kilograms of gold. All right, multiply all that and do all the maths, and it gives us a $470,000 loss, okay, for that month. And then we look at March. 25,600 kilograms of gold was exported. We do the maths, and it gives us a pretty big loss of $392,709,000, right, for that month. Okay, so if we were to do the total, it comes to $5,195,729.8023 loss incurred by Switzerland over 5 months due to imaginary local gravity. Okay, 5 million bucks. All right, but let's suspend our judgment for the moment and take a look at the gold exported by Switzerland to the 6 countries I mentioned earlier. Okay, so we'll get a fairly decent amount when we add all this up. So we look at Switzerland to China. There you go. That's how I worked out our the weight difference between the 2 latitudes, right? By subtracting China's latitude from Switzerland's and then multiplying that by the latitudinal weight variation, right? So in November to China, Switzerland exported 30,100 kilograms, all right, which gives them a $573,000 loss. Okay, it doesn't sound much. All right, but let's have a look at December. Then this is because of Chinese New Year. So anyway, in December, they gold exported was 154,100 kilograms, and it gave them a $2.9 million loss in that month. Okay, just that month alone. All right, so then we go to January 2017, 17,800 kilograms with a $339,097 loss, right? And then we go to February. There's 21,500 kilograms exported, which gives you a $409.5 thousand loss for that month. Then we go to March. 24,000 kilograms of gold exported, which equates to $457,000 loss for that month. And the total loss for the 5-month period was over 4 million, right? 4.7 million incurred by China over 5 months due to imaginary local gravity. Okay, and then we look at Switzerland to Hong Kong. November, 44,400, right? Which gives you a $3.1 million loss. Okay, then we look at December. 38,900 kilograms were sold, which gives you a $2.7 million loss. All right, December was a bad time for Hong Kong. Then we look at January 2017. 21,600 kilograms, which is a $1.539 million loss to Hong Kong. Okay, then we look at February. There's 7,200 kilograms that were sold. $513,000 loss in February. Okay, so not having a good 5 months. In March, 24,300 kilograms of gold was exported, which gave a $1.7 million loss to Hong Kong. Okay, big loss. So if we add all these losses for the 5-month period, we end up with a $9,720,910 loss incurred by Hong Kong over 5 months due to imaginary local gravity. Okay, now let's look at India. November, we get 61,300 kilograms, which gave them a $3.2 million loss on weight. Okay, December was 21,100 kilograms, which gives them a $1.1 million loss for that month. All right, we're talking big numbers here, much bigger than beef. All right, then we look at January 2017, 26,400 kilograms of gold exported, and we get a $1.3 million loss for that month. Okay, that's a pretty big loss for that month, but you might have thought that given those losses that India would stop importing gold from Switzerland. But let's continue with the figures for February and March, shall we? Okay, so we have a look at February. 37,200 kilograms exported, which gave them a $1.9 million loss. Okay, and then we get March. All right, 55,600 kilograms of gold exported, which gave them a $2.9 million loss, approximately. All right, using those figures. So a total loss for India is 10,586,748.3251 loss incurred by India over 5 months due to imaginary local gravity. That's a big loss. Okay, let's look at Switzerland to Thailand. In November, there was 4,500 kilograms of gold exported, with a loss of $434,000 worth. All right. Then in December, there was 10,200 kilograms exported, with a $984,000 loss. Okay, which is pretty big for Thailand. Poor Thailand, right? And then in January 2017, there was 13,800 kilograms of gold exported, with a $1.3 million loss. Yeah, that's right, $1.3 million loss for Thailand. All right, then we look at February. There was 3,400 kilograms exported, which gave them a $328,000 loss for that month. All right, then we're looking to March. There was 3,600 kilograms of gold exported, which gave them a $349,000 loss. Okay, so when we add that all up, we get a total loss for those 5 months of $3,429,151.7599 loss incurred by Thailand over 5 months due to imaginary local gravity. Okay. All right, let's look at the gold exported to Singapore. In November, there was 10,100 kilograms of gold, which led to a $1.3 million loss on their behalf in November. Okay. Then in December, there's 22,900 kilograms of gold exported, which gave them a $3 million loss. All right, $3 million. Okay, it's not a drop in the ocean. All right, then we've got January 2017. There's 13,600 kilograms of gold exported, and that gave them a $1.8 million loss, right, for January. Poor Singapore. Then we go to February, and there was 2,800 kilograms exported, all right, which gave them a $373,794 loss. Okay. Then we go to March. There was 6,100 kilograms of gold exported, which gave them an $814,000 loss for that month. So if we add all the 5 months together, we get a $7,409,133.4895 loss incurred by Singapore over 5 months due to imaginary local gravity. All right, let's go to the UAE. It's not as much, but November they exported 2,400 kilograms of gold, which gave them a $149,000 loss. Okay. And then December, 6,100 kilograms of gold exported, which gave them a $380,000 loss for that month. All right, in December. All right, then we move over to January. and we get a 3,700 kilograms of gold was exported, which led to a $230,000 loss for that month. Alright, they don't seem to export as much as the other countries. Then we go to February, 1,900 kilograms of gold, right, which gave them a $118,000 loss for that month. Then we move over to March, and we've got 3,100 kilograms of gold exported, which gives them a $193,000 loss for that month. Okay, poor UAE. Then we add all those together, and they get a $1,073,346.7332 loss incurred by UAE over 5 months due to imaginary local gravity. Okay, let's recap the losses. If we add all them up, it gives us $42,129,868.8015, right? Lost due to a local imaginary gravity, right? Why did they suffer that much loss? Right, because of local gravity. Rubbish. I call bullshit, okay? There's no such thing as local gravity, alright? Nikola Tesla said, today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. Okay, and that seems to be the case here, especially with the IGF and the FAC. They don't bear any resemblance to reality. Alright, so I call bullshit, okay? It's all bullshit. It doesn't work. Now the reason why I've updated this video is because on the other video someone kindly pointed out that the mass in regards to the IGF and the FAC wasn't right, that I'd misread it. Now on my part, it wasn't a deliberate misrepresentation. You know, I just in the hustle and bustle of trying to put things together, I just yeah, I didn't look into it enough. And but I am thankful for people who are willing to point out where I've gone wrong, and I'm willing to admit that, you know, it's in the name of intellectual honesty and integrity. I'm willing to admit when I've made a mistake, so that's cool. And yeah, they weren't able to find any problems with the rest of the video, so I'm pretty happy that only, you know, of 50 minutes of video, they could only find fault with about 4 minutes of it. Alright, so that's good. Still doesn't take away from the fact that you know, even if it does do a good job of representing the theory, it doesn't necessarily represent reality, as we can see from how international trade, especially the gold trade, would be affected by this. Okay, there would be a huge loss incurred in international trade if there was such thing as local gravity. Okay, local international trade would not even exist, because there'd be too much loss incurred on top of the transport fees and you know, everything to do with costs and import duties and stuff. It just wouldn't happen. Okay, I mean, no one will want to do international trade, right, if it was going to cause this much loss. So I'd say that's totally debunked. All right, now that's why I concentrated on this particular aspect. I mean, I could have tried to debunk NASA, right? I mean, you look at this guy in the ISS, right? He's on his treadmill and he's got this harness holding him down because he doesn't want to fly off or anything like that. But then you have a look at that pair of scissors, right? It seems to be defying gravity. What's the point, you know? That thing should be flying up and hitting him in the nuts, okay? And then you got this guy, he's on the ISS, and it's moving at 170,000 miles per hour apparently in orbit, yet he's not phased at all, is he? He just seems to be like waving, saying hi there, you know. And then you got this guy who's actually trying to do some maintenance on the ISS. I mean, if I could get someone to do maintenance on my car while I'm traveling at 110 kilometers per hour, I'd be happy, right? I could have debunked the heliocentric model. You know, I mean, you have a look at this picture here and it's the helical. See how it's not to scale. I mean, it's all science fiction. It's not real, mate. I mean, look at it. It's not even to scale. Okay, it's not even realistic. Even this one, it's not realistic. I mean, it's not even. It's definitely not to scale. This one's not to scale, and it's showing a little planet going in front of the sun, which would be obliterated. And look at this. Look at how they try to ascribe it. How close that planet would be to the sun. It's not even to scale. It's not realistic. It doesn't describe reality. Whereas you have a look at my picture here. That's actually to scale. There's the little sun on the left and the even smaller Earth. That's how much distance there would be between it. And then I could have debunked Don Petit, right? Now, he reckons that we can't go to the moon anymore. We used to be able to, but we can't because the technology was destroyed, right? He's basically admitting that they're not as smart as the NASA scientists of the 1960s who put this piece of shit on the moon, right? All right, and he says it's all cause technology, okay? He says the technology was lost and destroyed, okay? They're not as smart as they used to be, okay? That's bullshit, okay? Absolute bullshit. I call bullshit on this one. I could have debunked Einstein's relativity, all right? I could have had a real go at I might do that next video, and even the idea that the closest stars are like 40 trillion kilometers away from us. I could have debunked that, even though you know this apparent satellite picture or two of them show the stars between the satellite and Earth. Some people will say it's space junk, but this is black and white rubbish. Okay. Oh, it's because they're fixed. These stars are fixed, right? Even though they're still moving with us. Anyway, if you have a look at this, I decided to do this one experiment. If you have a look what I've done, I've got a container, just a microwave container. I've put water in it. I've tilted it by putting one end on the other end of on another smaller container. And as you can see, I've if you can see what I'm trying to do here, you'll understand. I mean, I've got a shaker top, a shaker lid off my Himalayan rock salt, right? It's just sitting on top of the water. It's not moving. I mean, you'd think that, you know, if water does sort of conform to a convex shape or to a tilt, then this thing would just be flowing, but it's not. It's level. That's right. Water maintains its level. It seeks the lowest place and then it maintains its level. All right, it finds its level. That's why they call it sea level and not sea curvature. Okay. Yeah, don't be stupid. Look at that, it's not even moving. I've had it for over a minute. It's just sitting there, level. Alright? It's level as. It's more level than my face, okay? Sorry, I just had to put that joke in there. My face isn't very level at all. It's close, but it's not close. It doesn't get the gold medal. So all in all, there's a lot of things I could have, you know, used to debunk the globe birth, but I thought, you know, the gold export would do it. All right, I mean, you just have a look at the figures. All right, $42 million loss over a 5-month period. That's a lot of money. Okay, so look into flat Earth yourself. Look into people who have put out different videos. Have a look at them. Do some research for yourself. Have a look at curvature, or look for curvature, the fake curvature, all right? And I just want to thank you for watching, okay? Peace out.